Hello, everyone. Today, I'm very glad to share my research with you. The topic of my presentation is human-robot collaboration for heavy object manipulation, kinesthetic teaching of the role of wheeled mobile manipulator. Human-robot collaboration significantly extends robotic systems applications when working in spaces like houses, hospitals, or laboratories. Employing a robot to replace an operator can help to avoid injuries and low productivity. As shown in the top two figures, human-robot collaboration involves an important problem, that is how to teach the robot the motion pattern of the demonstrator. Besides, inspired by how a human pushes a heavy box, as shown in the bottom figure, the robot can exert a bigger force by changing his pose. We can extend this concept to robotic operation. We try to obtain the maximum force exerting capability via kinematic reconfiguration of the robotic system, meaning to use the least joint torque output to obtain the same end effector force. Thus, two problems should be solved: motion pattern learning and force exerting capability enhancement. The printed figure shows the general diagram of manipulating an object using learning from demonstration method, which can be divided into three stages: lifting, carrying, and lowering, as shown in the top three figures. In the demonstration phase, a demonstrator teaches the robot how to handle the task with the user. The robot will then learn the demonstrator's task skills and can subsequently complete the task as shown in the bottom three figures. The lifting and lowering stages contain sizable force output in the vertical direction during movement. Thus, the impedance behavior between the human and the object should be learned. The carrying stage involves only the desirable compliant movement in the horizontal plane. Therefore, only the kinematic motion will be learned and reproduced. As shown above, we focus on two problems in this paper for human-robot collaboration. One is to learn the motion pattern of the demonstrator. The other is to enhance the force exerting capability in the vertical direction for payload handling tasks. The main contribution of this paper is twofold. For the motion pattern learning, GMM and a stiffness estimation-based approach are used to learn the impedance behavior in the lifting and lowering stages. GMN and GMR are employed to reproduce the kinematic motion in the carrying stage. For the force exerting capability, the directional manipulability of the manipulator is enhanced via the mobile manipulator's non-space, which is defined with consideration of joint torque differences. For the kinematic modeling, we first express the pose of the end effector in the manipulator reference frame, and then combine the mobile base to calculate the end effector pose in the world reference frame. We also provide the constraints for the mobile base and the manipulator. Usually, the manipulator is subject to holonomic constraint. Thus, we use its joint velocities as the manipulator generalized velocities. And finally, we can get the Jacobian of the WMM system. The Jacobian plays an important role in linking the joint velocity with the end effector Cartesian space velocity. The WMM is really redundant for a given task, which means there are more doors than the task needs. Then we can obtain the redundancy resolution for the WMM, in which the task space velocity can be derived using admittance control to guarantee compliance, and the non-space motion can achieve force exerting capability enhancement. This part is the kinematic control of mobile manipulators with directional manipulability enhancement. First is the definition of directional manipulability: to enhance the force exerting capability, which means achieving the same end effector force or torque using less joint torque output. Yuskava, etc., proposed the concept of force manipulability ellipsoid in order to realize force enhancement in any given direction. Task compatibility is proposed by Chu, etc. In this paper, we extend the concept of task compatibility with consideration of joint torque differences. Besides, we also minimize the influence of manipulator gravity by introducing sigma 2. The combination of these two functions is the optimization objective. The meaning of directional manipulability is shown in the top right figure, and the target of this process is to maximize it in the given direction through kinematic reconfiguration. Here we will introduce the method for learning and reproduction of the collaboration skills for object manipulation. As illustrated before, the manipulation process can be divided into three stages: lifting, carrying, and lowering. Since the lifting and the lowering stages require learning the impedance information, and the carrying stage only needs to learn the demonstrated trajectory, thus we provided two approaches to solve them. First, we use GMM to encode the robot trajectory in the demonstration phase. In the lifting and lowering stages, the trained GMM and the stiffness estimation technique are used to learn the demonstrator's impedance-based behavior. And in the carrying stage, the trained GMM and GMR are adopted to encode and reproduce the WMM position trajectory taught by the demonstrator. The block diagram of the control system is shown here. After obtaining the demonstrated trajectories, all the recorded data will be divided into three portions according to the three stages, and the required learning performance will be realized using the foregoing method. Then we will show the experimental results. The first is the results of force exerting capability enhancement in the vertical direction. The top left figures show the mobile manipulator's configuration before and after the kinematic reconfiguration. It is obvious that the second one is more suitable for carrying heavy objects. The results are shown in the top right figures. During the experiment, first a payload of 1 kilogram was added, and then a weight of 3 kilograms was applied. With the initial WMM configuration, when the 1 kilogram payload was added, all the joints could normally work. However, when the 3 kilogram weight was applied, the task stopped due to the saturation of joint 2. With the final WMM configuration, when the 1 kilogram weight added, the joint with maximum joint torque output was joint 2. When the payload of 3 kilograms was applied, the WMM could also hold it. The second is the result of human-robot collaboration for object manipulation with learn from demonstration. The final WMM configuration is employed to conduct the experiment, and the non-space control is also utilized here. We select 3 objects with 1 kilogram, 3 kilogram, and 5 kilogram to demonstrate the performance of the learn from demonstration method in object manipulation. Some pictures of the experiment are shown in the left figures. For each object, 4 demonstrations were conducted. The WMM trajectory and demonstrator's force in the vertical direction in 5 kilogram scenario are shown in the right figures as an example, and which would be used as training samples to train the robotic system. The top left figure shows the learning results for the lifting and lowering stages, where 10 components were used for each stage. Its bottom row presents the corresponding weighting matrices, which play an essential role in imitating the demonstrator's impedance in the reproduction phase. The learning results of the demonstrator's impedance in the lifting and lowering stages are presented in the bottom left figure. The learned models of the x-axis and the y-axis in the carrying stage are presented in the top right figure, where 12 components were employed, and the trained center and covariance matrix of each Gaussian model will be employed to derive the end effector's velocity according to its corresponding position via GMR. The position velocity profiles for x and y in the carrying stage are provided in the bottom right figure. The complete end effector trajectories for the reproduction experiment are shown here. In the reproduction phase, the WMM can cooperate with the user to conduct the object manipulation task. In scenarios of 1 kilogram and 3 kilogram, the object could be lifted 16 centimeters as we expected, and the desired horizontal displacement in X reached 0.9 meter. However, the displacements in Y only arrive at 1.26 meter and 1.31 meter for 1 kilogram and 3 kilogram payloads respectively. In the scenario of 5 kilogram, the motion displacement for X and Z was 0.848 meter and 15.6 centimeter, but the destination in Y was reached. This is the video of the research. First is the force exerting capability enhancement experiment. The WMM will change its configuration to improve its performance to carry heavy objects. The second is human-robot collaboration for heavy object manipulation. The left shows the demonstration phase, and the right shows the reproduction phase. The final part is the conclusions of this paper. In this paper, a method to realize human-robot collaboration for heavy object manipulation is proposed with a mobile manipulator. The main points are as follows. First, the redundancy of the WMM is employed to enhance its force exerting capability along the vertical direction to facilitate the carrying and transport of heavy objects. Second, GMM and stiffness estimation are adopted to learn the demonstrator's impedance behavior in the lifting and lowering stages. Third, GMM and GMR are implemented to reproduce the WMM motion in the carrying stage. Fourth, the effectiveness of the proposed approach has been experimentally verified with a four-wheel mobile manipulator by collaboratively manipulating a heavy object. That's all for my presentation. Thank you.